We'll move on now from polynomial equations to exponential and logarithmic equations. These are a little bit different in that our tools will be different. To solve exponential equations, we'll typically use logarithms. To solve logarithmic equations, we'll typically use exponentials. And this is because they undo each other. Recall that, in some sense, these problems are dual to each other. Y equals a to the x is the same as saying log base a of y equals x. So I use logarithms to describe a certain problem for exponential functions. And I'll also draw your attention to the fact that log base a of a equals 1, log base a of 1 equals 0, and a to the 0 equals 1, and a to the 1 equals a. Just our basic principles for exponential and logarithms. We might have to use these as we try to solve equations. So if you don't remember these properties, it can be difficult to do the last step for some of these problems. So let's take a look here. So suppose I want to solve the following exponential equation. I have 4 to the x minus 1 equals 16. So what do I want to do here? Well, I want to somehow get rid of this exponential. Okay? I want to apply a function to both sides of the equation so that I reduce the complexity of the problem. So I get rid of this exponential. So what does that? Well, recall that log base a of a to the x is just equal to x. So, or this is for any a. So if I want to get rid of this exponential with a 4 in the base, I need to hit both sides with log base 4. So I have 4x minus 1 equals 16. So this tells me that log base 4 of 4 to the x minus 1 equals log base 4 of 16. So what does this buy me? Well, the left-hand side becomes much simpler because I took log base 4 of 4 to the something. So those cancel out. And I just get x minus 1 equals log base 4 of 16. Now let's try and play a game with this. Is there a way I can understand what log base 4 of 16 is? Well, one trick we can use is to remember that 16 is 4 squared. And now use some additional logarithm tricks. Remember that if I have exponentiation inside, that can come out as a multiplier on the front. And now I remember what I just mentioned in the previous slide, that log base a of a is always 1. So log base 4 of 4 is 1. So I get that x minus 1 is equal to 2. And now I conclude that x is equal to 3. So for this problem, I had to use many different properties of logarithms. I had to use the fact that they cancel out exponentials here. And then I also used the property that exponentiation inside the logarithm comes out as a multiplier. And then the problem was pretty straightforward. So let's look at a problem with logarithms now. So here I want to solve the equation log base 2 of x is equal to 3. How could I do this? Well, I'll remember something similar to what I just did, which is that exponentiation undoes logarithms. So if I want to get rid of this log base 2, I have to hit it with an exponential. So I'll write that here. A to the log base a of x is always x. So I'm going to hit both sides with a, with 2. And now a wondrous thing happens. The left-hand side simplifies completely because I have 2 to the log base 2 of x. Well, that's just x. Incredible. The left-hand side has totally collapsed. And what is 2 cubed? Well, you can remember it, or you can write it as 2 times 2 times 2, so 8. So that's the complete answer here. This is actually even simpler than the previous example, because once I hit the logarithm with the exponential, there was no additional algebra on that side of the equation. X was just completely by itself. So a nice example. So here's one more to look at, which is an inequality. Okay? Let's think about this. I have e to the x greater than e to the 2x. I want to know for what values of x this is valid. So what can I do here? It's hard to understand because I have these exponentials. So I'm going to show you 2 ways to do this. One way is involving logarithms. So I'll do natural log of both sides, right? Because natural log is log base e, so it's the logarithm that undoes this. Okay. So what do I get? So here I get x. Now the left-hand side, it's not so obvious, right? Maybe something that I could do would be to bring the 2 out, or just recognize that when I take the natural log of e to the 2x, I get 2x, not x. But you can write this as 2 natural log of e to the x via the exponential rules. 2 to the x. So now I need, so just rewriting this, x is greater than 2x. So when does that happen? When 0 is greater than x. So this happens when x is less than 0. Okay? In that case, e to the x is greater than e to the 2x. I mean, of course, for negative values of x, they're both going to 0 very quickly, but e to the 2x goes to 0 more rapidly. So in that case, e to the x is bigger. So I'll say x needs to be less than 0 as the solution. Okay. One other way to do this without involving logarithms is the following. So we'll call this method 1. Method 2 would be to say multiply both the left and right hand side by e to the minus x. Then I get that e to the minus x times e to the x should be greater than e to the minus x times e to the 2x. So I get that e to the 0 should be greater than e to the x, aka 1 should be greater than e to the x. So when does this happen? Well, if I know the plot for e to the x, I see it's exactly when x is less than 0. Because the plot is like this, roughly. I mean, it's actually going towards 0 for negative values of x. So here the value is 0, 1. So I see that my solution set is everything over here. That's when it's less than 1. So 2 different ways to think about it. One is using logarithms. The other is using just the algebraic properties of exponentials. Both work, and I think it's worth understanding both of them.